In this calculus lesson, we're going to be taking a look at tangents and velocities. We're going to be examining the essential question, what is the connection between a tangent line and instantaneous velocity? The word tangent comes from the Latin word tangens, which means touching. A tangent line to a curve, then, is a line that touches the curve. In our two figures, in figure A, we have a circle with a line touching the circle or tangent to the circle at one point. In figure B, we have a function f, which is a curved function, and at a point P, we have a line that touches the curve at point P. Notice as this line continues, it intersects our curve at another point, but the line itself is tangent at point P. A tangent line then may intersect the curve at a place other than the point of tangency, but at the point of tangency, the tangent comes alongside the curve and just touches it at the point of tangency. The slope of the tangent line is said to be equal to the slope of the curve at the point of tangency. We can estimate slopes of tangent lines by finding slopes of successive secant lines that are near the tangent line. We can either choose to approach the tangent line from one side or the other side, or even from both sides simultaneously. Whichever method we choose, we arrive at the same limit. Let's take a look at an example. Here's example 1. We want to find the equation of the tangent line to the parabola y equals x squared at the point 1, 1. And we're going to choose a point xy on the parabola such that the point P is different from or not equal to point Q. So first thing we're going to do is we're going to find the slope of the secant line PQ. And we're going to use values for Q that bring it closer and closer to P. If you have our text, the text for our class, if you look at figure 3 on page 46, you'll see a visual representation and a visual animation in the text where you can see this. Okay, so here's our point Q. Notice that it's different from point P. Point P is 1, 1. Point Q has an x coordinate, and of course the y coordinate, since y equals x squared, would be x squared. We're going to choose some points for Q or for x to find our y coordinate for our point Q and find our slope. So let's do that. If x is 2, this ordered pair would be 2, 4. So x is 2, y is 4. And to find the slope from P to Q, we would just subtract our y coordinates over our x coordinates. So we would do 4 minus 1 over 2 minus 1. And when we do that, we get a slope of 3. Okay, at 1.5, 1.5 squared is 2.25, and we're going to quickly fill in this table. At 1.1, 1.1 squared is, of course, 1.21. 1.01 is 1.0201. And at 1.001, it's 1.002001. Again, finding the slope by subtracting the y coordinates divided by the difference of the x coordinates, we can do these very quickly. So here we would do 2.25 minus 1 divided by 1.5 minus 1. And I've calculated all those values, our various slopes as we go. As we bring point Q closer and closer to point P, these are the values of our slopes. Oops, this one has 2.001, and this one actually only has 2.01. One too many zeros there. Okay. But we can see that as Q moves closer and closer to P from points larger than P, x values larger than the x coordinate of P, we see our slopes gradually go from 3 down to something very close to 2. Let's reverse this and go the other direction, starting at 0. So our point Q would be at 0 to start with, and move it up towards point P at 1, 1. So here, filling in those values, 0 squared is 0, 0.5 squared is 0.25, 0.9 squared is 0.81, 0.99 squared is 0.9801, and 0.999 squared is 0.998001. Calculating the slopes, again subtracting the y-coordinates and dividing by the difference of the x-coordinates. So we'd have 0 minus 1 over 0 minus 1. We get, of course, 1. And doing the same thing for each of these points, 0.25 minus 1, 0.5 minus 1 would calculate all of these slopes. And we see that these slopes gradually increase until we get to our last slope, 1.999, which is very close to 2, just like from the other side, from points greater than 1, we had 2.001. So the slope of the tangent line is going to be the limit of the slope of the secant lines. We write, using some math terminology, LIM for limit. So the limit as point Q approaches point B of the slope of PQ. And let's go ahead and put our rule there. What is our slope for PQ? Well, it's x squared minus 1 over x minus 1. And we're finding the limit of that slope. And since this is in terms of x, the x coordinates that I chose to calculate my slopes were all getting closer and closer to 1. So we write the limit as x approaches 1 of x squared minus 1 divided by x minus 1, and we found that that value came out to be approximately 2. We'll actually find that it is exactly 2 as we learn how to do this using more exact methods. Example 2, we're going to estimate the slope of a tangent line not based on a function rule, but based on the numbers or the values in a table. The flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when the flash is set off. The data in the table describe the charge Q remaining on the capacitor, and that's measured in microcoulombs, at time t, which is measured in seconds after the flash goes off. We're going to use the data to draw the graph of this function, and we're going to estimate the slope of the tangent line at the point where t equals 0.04. So first off, let's get a graph of this. Our t values on our horizontal axis are all positive, and they go by 0.02, so let's go by a scale of 0.02. I'm just going to write every other one. So 0.02, 0.04, 0.06, 0.08, and 0.10. And our values along our vertical axis, our q-axis, have to go up to 100. So let's go by a scale of 10. Here's 50. And there's 100. And that's in microcoulombs. And our time t is in seconds. So let's quickly graph those points. We have 0, 100, 0.0281, and 0.04 is at 67, 0.06 is at 54, almost 55, 0.08 is at 45, pretty close, and 0.10 is at 36. These points, not quite in a straight line. They do curve very slightly. And note that the slope of the tangent line is going to represent the current flowing from the capacitor to the flash bulb measured in microamperes. That is, it's going to be in microcoulombs per second. Okay, so how do I estimate the slope of the tangent line at 0.04? That's at this point right here. I want the slope of a line which just touches this curve at that point. So right about there. And I want to estimate the slope of that dotted pink line that I've put in there. Well, I can find the slope between any 2 points on this curve by using the points in the table. And if I'm interested in what happens at 0.04 seconds, then let's find the slopes of the secant lines, or the slopes of the values that are closest to that point. So let's find out what happens between a time of 0.02 seconds and 0.04 seconds. Let's find that slope. So here are the 2 points that I want to work with. Excuse me, I want a comma there. 81.87. Okay. And of course our point of interest, 0.04 seconds and 67.03 seconds. So the slope of this secant line that connects these 2 points on the graph right here, it's going to be 67.03 minus 81.87 divided by 0.04 minus 0.02. And I've calculated that already. That number is negative 742.00. This is microcoulombs per second. Well, we have another point that's also very close to our point at time 0.04, and that's the point at time 0.06. So let's estimate that slope of that secant line as well. We have 0.06, 54.88 as one point, and of course our point of interest 0.04, 67.03. So let's go ahead and find the slope of that secant line, which connects these 2 points on the graph. So doing our slope equation, we're going to have 67.03 minus 54.88 divided by 0.04 minus 0.06. And I've calculated that slope of that secant. That value is negative 607.5 microcoulombs per second. So my slope of my tangent line is going to be somewhere in between the slope of these other 2 secant lines. Here's one, the slope is too steep. Here's this one, the slope is not steep enough. So the slope of the tangent line is going to be in between those. And since our best guess is somewhere in between those, let's just average these 2 numbers. So let's average our slope of these 2 secant lines. We're going to add these 2 together and divide by 2. And we are going to get then approximately negative 675 microcoulombs per second. Okay, a little bit of rounding there, but again, it's an approximation because we are averaging these 2 values and we cannot actually calculate the slope of that pink line. Now, we did it numerically. We could actually go to our graph and we can visually take a look at what this pink line looks like. I just sketched it in, so my approximation here may not be the greatest, but if I take a look at changing from, say, this point to that point, I can also estimate the slope of that tangent line. So let's take a look and see what those points are. At 0.02, it looks like we have about 50, 60, 70, about 78 maybe. And our point here at 0.08. Looks like it's at about 10, 20, 30, maybe 40. And so visually I can subtract and calculate the slope between those points. When I do the slope there, it looks like I'm going down. What are we going down? 10, 20, 30, 40, and over 1, 2, 3 over 0.06. And so if I divide those numbers roughly, I would get negative 667 approximately, and that is in line with our example that we have from our table of values. Okay, let's do one more example. We said this lesson is going to answer the essential question, what the connection is between tangent lines and velocity problems. And so now that we've talked about tangent lines, let's take a look at a velocity question. So suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto. It's 450 meters above the ground. We want to find the velocity after 5 seconds. So we want to know what happens at exactly 5 seconds. The equation for free fall, neglecting air resistance, is S of t equals 4.9 t squared. And of course, average velocity is defined as the change in position divided by the time elapsed, or the elapsed time. So we're going to use successive approximations of our average velocity to estimate the instantaneous velocity at 5 seconds. So let's create a table of values, kind of like what I did earlier, and let's see what we can come up with for our approximation for our instantaneous velocity. I've already created this table of values, so we're just going to very quickly write it down, save a lot of time. And I want the slope, which of course is change in position divided by time elapsed. And I'm interested in what happens after 5 seconds. So at 5 seconds, plugging 5 into our equation, 4.9 t squared, I have the ordered pair 5, 122.5 feet. So at 5 seconds, the ball that has been dropped from the tower has fallen a distance of 122.5 feet. Let's see what happens at nearby points. Let's see what happens at times approaching 5. We'll start at 6, and we'll move right on down until we're very close to 5 seconds. And our distance that the ball has fallen at 6 seconds is 176.4 feet. I'm just going to fill in those other values because I've already calculated them. And we're going to go from there. Notice that I don't round any of those numbers. I want to keep these numbers so that when I do the division by very small numbers, I don't lose any accuracy. So we'll do some rounding when we get to the end, but we're not going to do any rounding until then. Now our slope, remember, change in position divided by time elapsed. So I'm going to do my change in position. I'm going to take 176.4 minus 122.5 all over 6 minus 5, or 1 second. And so I've calculated all of these slopes, and I'm just going to fill those in. We can see the progression of these slopes getting slightly smaller each time until they all seem to approach 49 feet per second. We can do this from the other side, taking times not greater than 5, but times smaller than 5, and working up to 5 and calculating those slopes as well. So starting at a time of 4, and then 4.5, 4.9 seconds, 4.99 seconds, and finally 4.999 seconds. Using our rule, 4.9t squared, we can calculate the position, that is how far the ball has fallen at that elapsed time. Here we have 78.4 feet, and I'm going to fill all of these in because I already know them as we move up. And once we have these values, we are going to calculate the slopes. Again, slope is found by change in position. So from 4 to 5 seconds, our change in position is 122.5 feet minus 78.4 feet, all divided by an elapsed time of 1 second. And that turns out to be 44.1. Calculating these slopes, and more slopes. And as we see, these slopes are gradually increasing until they reach the same limiting value as the slopes from the other side of 49. So at 5 seconds, we have found that the instantaneous velocity of the ball is 49 feet per second. Okay? One last thing here. In general, we can write an expression for the average velocity or the slope of a secant line between any 2 points on a curve. So suppose I have a curve right here and a point P and a point Q, using our same rule here, S equals 4.9t squared. If point P has an x-coordinate of A, and I move just to the right a little bit, so now I'm at A plus H. Of course, the distance or the difference between that is a distance of H. And then we go to our point Q. So P has coordinates A, F of A, and Q has coordinates, x-coordinates A plus H, and F of A plus H. What we can do with that is we can write an equation in general for the slope of this secant line. So our slope of the secant line, change in y or position divided by change in x or time, we have f of A plus H minus f of A divided by the change in our x-coordinates, A plus H minus A. And in our denominator, the simplify, the A minus A adds up to 0. So we have f of A plus H minus f of A, all divided by A. This is a general expression for the slope of a secant line. The limit of this slope of this secant line, remember the slope of this secant line is average velocity because it was a change in position divided by a change in time. And if I take the limit of the average velocity as the A plus H value, as this value slides closer and closer to point P, we end up with the slope of the tangent line, which is the instantaneous velocity at A. And so that's our connection between the slope of the tangent line and the velocity. We found that the instantaneous velocity is equal to the slope of the tangent line at that point.